Okay. As I was saying, Chapter 3. And what did I say? Atomic structure. This is going to be the introduction to the mole. Have her write a pass for you. I'll sign it. It's going to be the introduction to the mole, but the rest of the year we're going to be dealing with the mole. The mole is chemistry, at least at the first year and even the second year level. Okay, it's all about the mole. Just remember that. Okay, before we go anywhere, a lot of this stuff I'm hoping is review, so I'm going to go relatively quickly, although there are pieces of it that are not going to be review, so I'll slow down a little bit for that. And then, could you sign that real quick? Thank you. My name. So what we're going to do is we're going to look at one of the blocks on the periodic table. I'm just going to randomly pick, actually not randomly, the element chlorine, which as you all know has the symbol Cl. And many periodic tables have other information on there. Many of them will have the atomic number. We'll get to that. They'll have a number. Oh, by the way, you'll want your periodic table out in front of you probably nearly every day for the rest of the year. So just like you take out a pencil or a calculator, you also need the periodic table. A lot of times there will be a number, another number. A lot of times that will be also located immediately below the symbol, and then usually below that there is the name. Okay? Now there might be other information on, depending on what periodic table you're looking at, there might be other information on there. But in general, this is the stuff that will typically be on any periodic table. I think that matches fairly well with what you guys have. Things might be in a little bit different position, but okay. Anyway, so what does all this mean? Well, as we just got done saying, this is the symbol. This is the name. This is the atomic number. And please listen and make sure you're distinguishing as I do this next one. This is the average atomic mass. Average atomic mass. That's where we're going to be spending a lot of our time. Okay, does anyone recall, you've learned some of this, yes? No. The atomic number, what information does that provide? It is the number of protons. Now, if it's a neutral atom, meaning it has no charge, that means it's also the number of electrons. Okay. Obviously, if it is an ion, then that is not going to be true, and that's a whole other thing that we're going to be talking about. You guys probably have heard this before or been exposed to this piece before. Okay. Symbol you got, name you got. Now, this average atomic mass thing, I'm not sure the extent to which you were introduced to that. I don't even know if you used those before. Does anyone recall using those numbers off the periodic table? It's possible you did. You did?
Yeah, but like very little.
And possibly to get to here? No. Okay, for something else. Okay, that's all right. I'm just kind of curious what that does. It doesn't matter. You don't have to tell me. So what is the average atomic mass? Well, it is the weighted average of the masses of the isotopes. Okay, now we've got some terms up there that you may or may not be familiar with. Does anyone know what a weighted average is? Every year that I ask that question, every class I ask that question to, I get many students that just look and stare blankly into space like so many of you currently are, and or go, I have no idea, which is really weird because that is how your grade is determined in this class, and that is how your grade is determined for your overall grade for every class at the end of the year. They're weighted averages.
So just like in this class, like quizzes and tests are worth a certain percentage.
Quizzes are worth a certain percentage, tests are worth a certain percentage, labs are worth a certain percentage. Now, there's 3 categories there. Well, actually, there's 4 categories. Okay, there's the written assignment thing too. Okay, if it were not a weighted average, if it were an arithmetic average, or sometimes called a straight average, what would each of those components be worth? 25%. Is that the case? No, they're each worth a different weight. Therefore, the weighted average. Okay, so. We're going to get to that. In fact, that's a whole big can of worms that we're going to open up here in a little bit, but I just wanted to make sure that you guys understood what a weighted average is. And then, so here's that word. You guys are very clear on that now. And then for your, I'm not going to go ahead and write a definition down for that because you guys, I think, clearly understand that. You also knew that each you get your overall grade at the end of the year for a class, an overall percentage. How was that determined? Yep, each quarter is worth 20%, and each exam is worth 10%. So everything's got a different weight. Okay, so you guys clearly get this. Now, what about isotope? It's possible you were not introduced to this. That does not ring a bell. Ion, you guys have heard of, yes? Isotope, no. Okay, so here's what an isotope is. It's easier if I define them in the plural, so I'm going to put isotopes. Isotopes are atoms of the same element with different mass numbers. Atoms of the same element with different mass numbers. Are there any words or phrases up there that you're unfamiliar with in that definition? Sam says no. Everything works out. Sam, what is a mass number? You know what mass is, you know what number is, but the mass number, let's make it easier. Where on the periodic table would one find the mass numbers for the isotopes of the elements? Good answer, everyone. They aren't on there. Yes. So this is what I'm saying. What is on there is clearly the weighted average of the mass numbers, okay? But the mass numbers are not individually on any periodic table, okay? So, what is a mass number? It is the sum of the particles in the nucleus. Now here I'm relying on either prior information that you guys have had in other classes since about 6th grade or so, or the little activity that you guys turned in yesterday. What are the particles in the nucleus? That's it, protons and neutrons. By the way, those are pretty standard symbols for protons and neutrons, a capital P with a plus sign, a capital N with a little 0 superscript. We'll come back to that. I actually skipped something already today, so we'll come back to that here in a second. But anyway, the sum of the particles in the nucleus. Now here's what's... Many of you aren't quite ready to make the leap of understanding quite yet. But if all of these things are true, the average atomic mass for any element is always the same. The average atomic mass is always the same. The atomic number is always the same for any given element. In fact, that's how we identify the element. It's got 17 protons, chlorine. If it has 18 protons, it's argon. Okay, so the atomic number identifies the element, or the number of protons identifies the element. But now I'm telling you that, wait a minute, isotopes are atoms of the same element with different mass numbers, and the mass number is the number of protons and neutrons. Yes? That is precisely it. Most, I'm not even going to say most. Yeah, let's go with most. Most of the elements have more than one isotope. There are some in which that isotope is the only thing, but most of them have multiple, which is why we have to take the average. So, for example, chlorine has 2. They are chlorine 35 and chlorine 37. Now, the values that I just wrote down there are the mass numbers. I shouldn't put a plural because that's only one. Okay, so when I write chlorine-35 or chlorine-37, those numbers represent the mass number. There's other ways to, there's other ways to indicate this. Can I erase this at all? You guys good there? All right, here's other ways to represent this. I could do it this way. Be comfortable with both of those. And actually there's a third. And probably the one that gives us the most information. Because we have to know something here. Or at least have a periodic table available to us so we can figure this out. Because if I ask you right now, how many protons does chlorine-35 have? Hopefully you would all tell me 17. But then if I ask how many neutrons, you would have to subtract, right? Okay, so you would have to know the 17 part. Or, this is what we call a nuclear symbol, by the way. We can do it like that. So obviously the upper left-hand corner represents the mass number, where the bottom left-hand corner represents the atomic number. Now, I don't know if we're going to have time to get there today. I would like to, but I don't think we're going to have time. There are some times there will be some information written up here that would be the charge if it were an ion in the upper right-hand corner. You've probably seen that before. If you guys did anything with naming and writing formulas when you were in your physical science class, it's possible you got used to writing the charges of the ions up in the upper right-hand corner. Becca, did you have a question? Or were you stretching your arm was like this? No. Okay. All right. So anyway, so in this case, if I were to ask you how many, do this. Okay. If I ask you how many protons were in chlorine-35, you would all obviously tell me 17. If I ask you how many neutrons, you would tell me 18. And if I asked how many electrons, you would tell me, say this again, 17, because of that, right? There's no indication that there's a charge that would also be 17. Is this stuff that you have done before? Some of you have, some of you haven't. Okay, this is why we go through this, make sure everybody's on the same page. It's not incredibly difficult, but we do have to make sure that we are clear on this. Now, doing the same thing for chlorine-37. What would my number of protons be? 17. Same element, right? Has to be 17. How many neutrons? 20. And how many electrons? 17. Everyone hunky-dory there? Okay. All right. So now, how do we get from these to this? Now, just for fun, this is a relatively simple question. I think you guys will get it. One of those isotopes, the chlorine-35 or the chlorine-37, in nature is more abundant than the other one. Which one is it? Chlorine-35, because the average is closer to that. You guys get that, right? There is not a single atom of chlorine that exists in the universe that has that mass. Because what is that mass? It's the average. They're either chlorine-35 or chlorine-37. And as it turns out, those isotopes are relatively distributed. When I say equally, I don't mean 50-50, but what I'm saying is if I go grab some chlorine over in, pick a country, pick a continent, I don't care, India, and grab a handful of chlorine atoms over here in the United States, the percent of chlorine-35 to chlorine-37 is going to be the same. There are some atoms where that is not the case. It's kind of weird. I am not going to hold that to you or hold you to that, and it doesn't really come up very often. However, if you were really, really into very finely tuned research type things, you might have to care where you were. But in general, they're fairly, the percentages turn out to be almost exactly the same everywhere. I believe this table actually addresses that. It might not. Hold on. No, there is a table that you will see at some point in time that actually addresses that information, but we will go, for the intents and purposes of this class, that the percents are going to be the same wherever you happen to find them. Okay, so now the question becomes, how do I get from here to here? There seems to be some information lacking, which is the what? Yeah, the actual percent, the distribution of these. So that's where we're going to head next. Does anyone have any questions before I go further? For the most part, I think probably 90% of that was review, with the possible exception of what the average atomic mass was, or what it represented, and what an isotope was. But everything else was fairly review. All right, moving on. This next stuff is not hard at all, especially for you math geniuses. But it does help you understand, hopefully, a little bit more about how your grade is affected or calculated, if you get anything out of it. This next piece, calculating percent, sorry about that, I lied. Average atomic masses from percent abundances. Nice little title there, huh? One way or another, you're going to have to be, if this is all the question is, calculate the average atomic mass from percent abundances, the information is going to have to be provided to you somehow or other. This first one I'm going to do, I'm going to just pretty much straight up tell you what to do here. As it turns out, chlorine-35, the species of chlorine that has 17 protons and 18 neutrons, has a mass of 34.969 AMU. That is not a bird-like creature found in New Zealand, which would be an emu. Anyone want to take a stab as to what AMU might stand for? Look at that. Nearly every year, I think every year, somebody gets that right. Nicely done. Okay. That is a relative mass. Okay? That is a relative mass. This is where I screwed up. I knew it was going to happen. I forgot to go over electrons, protons, and neutrons with you. Oops, my bad. I know that you guys are aware of electrons, protons, and neutrons. In that little packet, did you guys have to actually write the masses of those things in there? I know they're in the book. Did you actually have to write the masses down to answer one of the questions? And this is where I screwed up. All right, I need to go back and do that because that's important with our discussion that we're going to have here in a second. Anyway, an atomic mass unit is a kind of defined unit in which all of the other particles are compared to that unit. Okay? As it turns out, all of the masses of the elements on the periodic table are all calibrated to one isotope. And that isotope has actually changed over the years. It used to be one element, then it became another element, and now it's honed in on this one element. So all of the AMUs, all the atomic masses that we're referring to, are all based on carbon-12. Turns out there are 3 isotopes of carbon. You're probably aware of one of them. The one that's the least abundant, I believe. Okay, say it. I will not make fun of you. Pardon?
I was just overly made fun of.
Oh, okay. Fair enough. Yes?
The one I hear the most about is carbon-14.
That would be the one. Was that what you were going to say? That's okay. It's a good thing you kept it to yourself, right? Yeah, carbon-14. That's the one you hear about the most. Why?
They use it for carbon dating.
What does that mean? Do you date carbon?
No, judging how old.
Okay, you can use carbon-14 to help determine how old something is, and usually it's organic matter because of all the carbon, okay? Carbon-14 is radioactive. It has a decay rate. That decay rate is very, very well known. So by knowing what that rate is, how much carbon-14 is still present in a substance, you can kind of work backwards to figure out approximately how old it is. If you kind of think about that, that's not that difficult, okay? Oh, and also a small amount of knowledge of how much carbon should have been there because, for example, us. We haven't, the amount of carbon in us relative per person is a pretty standardized proportion, if that makes any sense. So assuming those things are true, you can kind of figure out how something old is. So yes, carbon-14. However, it turns out that is a very, very small percentage. It has a very small relative abundance or percent abundance. And then does anyone want to take a stab as to what the other one is, since I've kind of given you a hint and left a space? Carbon-13, okay? Also a very small proportion of all the carbon that exists, but it's not as radioactive, and so it's not as useful for doing the carbon dating. And again, we can do this. Which of the three is most abundant, do you think? Because the average atomic mass is 12.011. Clearly, by far, the most abundant. Okay, so anyway, where I'm going with this is all of the atomic masses on the periodic table are calibrated to carbon-12, or relative to carbon-12. Carbon-12 has how many protons? And how many neutrons? Okay. Right. In order to get to 12, you need 6 of each, right? If atomic number is 6, then we need... All right, so anyway, I'm now going to have to back up. Sorry about this. I knew I screwed up as soon as I went to another step, and my bad. This is a little aside because I messed up a little bit. Obviously, I think we're all clear that these subatomic particles are, in no particular order, proton, neutron, and electron. I think you're all pretty comfortable with these ideas. Okay? I've already shown you a symbol for the proton. Actually, I've shown you the symbol for all of them. Nobody asked me about that one, but there you go. Protons, neutrons, electrons. The mass of a proton, 1.67. I'm going to do this. Actual mass. 1.67 times 10 to the negative, and it depends what unit would you rather be in. Would you rather be in grams or kilograms? Kilograms? 24th grams. 1.67 times 10 to the negative 24th grams. You guys can't even imagine how small. It's just unimaginable how small that is. The relative mass. One AMU. Now, this is, I'm going to put some numbers down here. That's only to 3 significant figures. If you wanted 3 more significant figures, it would be 1.67242. There's a reason why I'm going there. Okay? This also becomes not exactly 1 AMU. It becomes, actually that is exactly 1 AMU. My bad. What is the charge on a proton? Positive. I mean, I think you guys have been fairly clear on that. Okay, neutron, actual mass, 1.67. I'm going to give you 3 more significant figures. 493 times 10 to the negative 24th grams. So it is slightly more massive, but barely. And relative mass. Anyone want to take a stab? to one significant figure especially, it is also 1 AMU. This is why when I'm giving you guys the mass numbers, that's why they're whole numbers. Proton has a mass of 1, neutron has a mass of 1. What's the average? What's the mass number for, chlorine? 35. For chlorine 35, it's 35. All right. Anyway, electron, actual mass. By the way, what's the charge on a neutron? It is neutral. It has no charge, and then in charge of an electron is 1 negative charge. Okay, so actual mass, 9.11 times 10 to the negative 27th grams. So around 1,000 times less massive than a proton or a neutron. So what is the relative mass? Well, because, and this is kind of similar to that idea, and I forget who it was I did this to way back at the beginning of the year, when I went and acted like I was going to pull a hair out of somebody's head and asked how their weight was going to change, and we determined that it wasn't, okay, because of the weight of the mass of the hair was so small. Same thing here. We are assuming that the electrons are not contributing a significant amount of mass to the overall. Now, here's an interesting question. Why the difference in mass? It is a small difference, but why the difference in mass? Here's something you probably did not know. What is a neutron? Let me go one step further. Did anyone remember studying radioactive decay at all in their physical science classes or some other class at any point in time? Does anyone vaguely recall the types of radioactive decay, what the particles that are produced are? Here comes Gracie to get her Gatorade. Because we're acquiring knowledge, we are trying. Yeah, the rest of them quit.
Really?
Yeah.
What did I do? Wouldn't surprise me if it was that.
Bye, Gracie. What was my question? Radioactive decay. What are the types of radioactive decay? Alpha radiation, beta radiation, gamma radiation. Does anyone recall any of these things? You may have been introduced to them. Okay. An alpha particle. This is actually, you guys know, you should know what an alpha particle is now. You just read about it and wrote possibly a couple of, what is an alpha particle? It is a helium nucleus. An alpha particle is a helium nucleus. Now, what's in a helium nucleus? Good. Thank you, Sam. Exactly. 2 protons, 2 neutrons. Nicely done. What is the charge on a helium nucleus? Sam? It's positive, okay? Because there's no it's a helium nucleus. Okay? So it's positively charged. So in alpha particles are positively charged because they're helium nuclei. Okay? A beta particle is an electron. Therefore, its charge is negative. Okay? Where did that electron come from? No. It can. But what? An eon? Oh, neon. No. Okay, good try. That's a good try. That's actually a somewhat, there was an attempt at logic there. Helium, neon, right? That's not what you were thinking? Oh, okay. Okay, so I tried to make sense of what you were saying. It didn't work. No. A beta particle, like I said, is an electron. It's negatively charged. It comes from the nucleus. Wait a minute. What are the particles in the nucleus? Protons and neutrons. So where'd the electron come from? Please look at the masses that I gave you for the proton and the neutron. What do you notice? What? A neutron is more massive, slightly. I know. A neutron is slightly more massive. Why? Come on. I've given you all the pieces. Boom! There it is. So what is a neutron? A proton and an electron combined together. That's why the neutron is slightly more massive than the proton. And to get beta decay, beta radiation, the electrons are not coming from the energy levels, because that would just be forming an ion. The electrons are coming from the decay of a neutron into a proton and an electron. The electron gets ejected, and now we have a new element because we have more protons. This is all kind of fun stuff, isn't it? But wait, it gets better. But anyway, so I just wanted to put that out there for you guys to recognize. So there's the subatomic particles. And then gamma radiation is just energy, which you guys haven't done anything with photons yet, I'm going to guess. We will in this class. Okay, so gamma radiation is just the energy. Anyway, mass of 34.9 or 969 AMUs. You know, even though I screwed up, I kind of like how it worked out. I think it's all coming together fairly well. And this has a percent abundance of. Well, remember we said this is going to be the one that's the most abundant because the average we already know is closest to is 75.77%. So that means of all the chlorine that exists out there, 75.77% of it is chlorine 35. Chlorine 37, on the other hand, has a mass of 36.966 and has a percent abundance of because there's only two isotopes, that's relatively easy to figure out. 2-3, my bad. Okay? Obviously, we didn't get to the point of actually doing the calculation. We will start there tomorrow. But I thought that went well. You guys did a nice job. Thanks for playing today.